Hey guys, this is going to be part 4 of the USB hub series. Sorry it's taken so long. Honestly, this project's been kicking my butt. I really wasn't expecting it to be this involved. And if you're in the Discord, if you're not, link is in the description. If you've been following along what I've been posting on there, I've been kind of talking about it. It's been really involved. I was expecting it to be, but a lot of the power management side, which this video is going to talk about, was a lot more involved. I definitely see why there are not a lot of full power hubs on Amazon or anything. They are just really, really power hungry. Obviously, 5 volts, 3 amps output. Doing 4 of those is a lot. But anyway, here it is. So this video, I believe I'm going to just stick on talking with kind of the overall power management scheme and the buck converter specifically. And then in the next video, which will be the final video for the schematic, that will cover mainly the input power filter and then the TVS diodes and protection for the downstream ports. So looking at the schematic, I'm going to just go into kind of a little recap of where we're at since, again, it's been a while. And one change I made to the USB-C to the MUX, someone, I think actually a couple people, but one person opened up an issue on Git. I had flipped one of the TX, RX 1 and 2s, I forget which. So that is fixed on here. Basically, we have the Type-C upstream facing port coming in. We have the AC blocking caps. Then it goes into our MUX, which our MUX takes the 2 sets of differential pairs. Depending on which way the CC pins are, it routes them out the output of the MUX. Then it goes into the actual hub, which obviously acts as our hub or switch to the 4 downstreams. For the downstream ports are all filtered with TVS diodes and some bulk capacitance. Those I'll get into, like I said, in the next video. And then the power for each of the downstream facing ports is handled in this VBus monitor, which I will get into towards the end of this video. Ultimately, when I was working on the schematic for this, there were a couple different ways that I thought that it could be approached, since the output power or the bulk of the power of the entire board is obviously going to be on the downstream facing ports on the USBs themselves. That is 5 volts. So typically, if you have something where the vast majority of power is at a single voltage, that's ideally what you want to have coming in the board. The problem is that would make it like a 20 amp or so input supply, which for a lot of reasons, least of all, or not least of all, is the size of the power converter, the AC to DC, just wasn't going to be practical. So I figured that probably wasn't the best way. And then trying to limit the input current, I decided on a 12 volt input. Realistically, I could have also gone with 24 volt to reduce the input current, but from what I saw, the power supplies were about the same size at that point. Because once you get to 12, 24, and 36 volts, the size is based more on just the power, and obviously the power in isn't going to change, it's just the current, but the difference going from 5 volts to 12 was pretty substantial. So I settled on 12 volt input supply, and then for the 5 volt buck, since again that is max power here will be 3 amps, so technically we could have up to 12 amps. Probably never would happen, because you're not ever really going to have 4 ports using all 3 amps each at any given time, but I tried to do my best to spec it to be pretty close to that. That's a lot of current. So the buck for the 5 volt had to be pretty beefy, and my original thought was to split it up into 2 bucks. And what's cool about having this all on Git is I actually have like two previous revisions of this to where I was using split 5-volt bucks. But the issue with that is the V-bus monitor, which handles overcurrent and short circuits on the V-bus lines, that handles obviously the overcurrent situation. So there was really no need to split the 5-volt buck into two. It was just redundant because one buck would feed this V-bus, which limits the current, and then the other would feed the other. But if it was just a single buck, it would still go into here, which are limited on the output side. So did it make sense to me? I do think it's a viable approach, but having two increases your EMI, it increases the amount of parts, and it just increases complexity. So I settled on a single 5-volt buck here, and then we also need a 3v3 output and then a 1.15 volt. Before you get to any type of specking, like if this was going to be another buck or an LDO, you obviously need to see what your current consumption is going to be. For the mux, it basically draws nothing. The USB hub in the datasheet, they have a nice little chart which has a formula for how much current it draws at what speed and how many ports. So by using that, it draws a decent bit at 3 volts, and I guess technically it should be 3v3. So it draws a little bit at 3v3, but it draws quite a bit at 1.15. Not much power, but since it's a lower voltage, it draws more current. So that is the main current draw on the hub, and then obviously the 5-volt draws a lot. So knowing that the 3v3 only draws 400 milliamps, I figured it was meaningless, or would it make sense to do a buck for that? So the 3v3 output is simply an LDO, load dropout regulator. So that comes from the 5 volts. So it's only dropping from 5 volts to 3v3. And since it will never be above half an amp, that's very, very little power being dissipated. So that was the easiest for that. And then the only other consideration is what are the bucks, what bucks would be used for the 5-volt and then the 1.15. So the 5-volt buck obviously is the more difficult one, solely due to it having to be rated at 15 amps, which goes without saying is quite a bit. For something that's this high powered, it's pretty normal to have the high and low side FETs external, because if they were internal, it would just need a lot more thermal dissipation, and you can have a lot more surface area on a external FET. So that's why these two are here. And then everything else on here is pretty bog standard for a buck. The one issue with this is the datasheet was absolute trash. So really the only way, like determining the ripple, if you needed to use a feed forward capacitor, stuff like that, really the only information they showed was on the design docs at the end, which aren't like official TI documents. So I leaned pretty heavily on the WeBench simulator for this, which I think actually for the video is pretty neat because it shows, honestly, a lot of times you don't want to get bogged down in tons of the calculations for these bucks, because the calculations are only as good as whatever they were based on. So they're a good start, but WeBench I have had really good luck with in the past, and then nothing is going to replace actually getting it on your board and testing it. So I do my best to not go super, super crazy with input capacitance, output capacitance, doing all the calculations. But I do want to go into how I use WeBench and some of the really big pitfalls that I think TI needs to fix in that. And it's a couple of things that has messed me up in the past. So on TI's website for the Power Designer, I think they've been changing the name from WeBench to Power Designer, but either way, we enter in the part number and it'll autofill the main inputs, minimum, max, and then nominal. I usually, without knowing the exact spec of the AC to DC converter that we'll be using, I like to just do like a volt above, a volt below. Output, we don't really have a nominal because we don't know exactly what it'll be normally. So it runs a simulation and then it will give a reference design like the one shown. And you can go through all of the values and choose alternatives. And based on whatever simulation, whatever SPICE software they're using, what are the recommended limits? And you can go and choose anything in here. And if it's not there, you can create a custom part. It's really neat. But the biggest pitfall, like I was saying before, is they use a I don't know what type of derating for their capacitors, but whatever it is, it's wrong. It's flat out not accurate. And this is something, it might come as a surprise to some of you to hear me say derating capacitance. So, something that a lot of people don't know is when you're using a ceramic capacitor, all capacitors kind of do it, but it's really only an issue with ceramics. If you are using it at any sort of DC voltage, it's going to have what's called a DC bias and you lose capacitance. So this tool is another amazing software. One of the coolest things that any company out there has. It's called SimSurfer by Murata, whatever. And they basically have detailed specs for every single one of their capacitors, inductors, I think some chokes and some other stuff. And it shows you what the DC bias is. So this is a 22 mic ceramic capacitor, rated voltage. Let me get one that's more realistic for what people would use. So here is a 10 microfarad, 25 volt X5R 0603. So super common part. And let's say you wanted to use it at the input of this converter because 10 mic, it's rated for over double what the 12 volt input is. So you're properly derating it for that. It's an X5R. So you're thinking, okay, it's not going to change over temperature. But at 12 volts, your effective capacitance is 1.5 microfarad. So if you go and design this based on this capacitor, you're going to have 4 mics on the input side when this requires 15. You're going to have all kinds of issues, not least of which is incredible input ripple. You won't pass EMI testing and potentially your whole converter won't work. So the issue I said with SimSurfer or with WeBench is typically what? You would take this part number and say, okay, derated at 5 mics, good to go. I don't know where they get their derating value from because if we search for that exact part number that they're using on WeBench, 25 volts, 10 mic, it's an 805. And you look at what the DC bias is at 12 volts, you will see that it is 1.7 microfarad. So if you blindly follow WeBench, for whatever reason, they just, I guess, don't care or have some weird algorithm for the derating here, it's not sufficient. So what I do in the way that I calculated this is I saw that it needed a minimum of 15 microfarad of capacitance, low ESR because they want ceramics. Obviously, for the input side, you need low ESR. And with the input side, you can never have too much high frequency capacitance. You can never have too low of ESR. So you don't have to worry about using the wrong type of ceramics as long as you have enough capacitance and you do the layout properly. So on SimSurfer, what you can do is go into advanced search, enter in DC bias, enter in your capacitance, and this is kind of a goofy thing. I've used this for quite a while, so I know kind of its quirks. Basically, you enter your DC bias, you enter in the max range of capacitance that you want, and then it's going to pop up a new table what your effective capacitance is. So now, if you want to use, say, an 0603, a 1206, whatever, you enter this in. You can enter in your effective capacitance, but what I typically do is for a 12 volt input, I want it at least to be 25 volts, but realistically, based on your effective capacitance, it will probably need to be higher. And by doing that, and going through and kind of seeing which ones were out there, I came to this part, which has a effective capacitance of 3.8 microfarads at the 12 volts. So that's why I use 1, 2, 3, 4, 5. So 5 times 4-ish is about 20 mics. So they want to have 15. This now has around 20-ish. Oh yeah, I have it written right there. So now our input supply is good. So I would say honestly, you see a lot of designs and app notes and stuff about switching supplies and pitfalls and everything. You never hear about DC bias being an issue, but it is a massive issue because everything those app notes are saying about how much input capacitance you need is fine and dandy, but if you're basing it on what the value is spec'd for under no DC bias, you're screwed. It's not going to give you that much capacitance. So there's my rant aside. That's the biggest gotcha with WeBench. Everything else is pretty straightforward. It specs, obviously, what FETs, and then again, it will give you alternatives for the FETs. It only really gives you TI options. They don't give you the range because realistically, most FETs will work here as long as the gate to source voltage is, the turn on voltage is good enough and it's rated for your current and power dissipation. VCC is just a internal supply, your bootstrap capacitor, your current limiting resistor that sets when it will shut down. Then another gotcha that that is pretty commonly talked about is your output capacitors. They do matter if they are too good, if the ESR is too low. So the way the feedback loop in one of these buck converters work is on the output of the inductor, and I believe one of the charts will show that. So the V out peak to peak. So this is what basically the peak to peak or the ripple on the output side. So right here on the output of the inductor is. Your feedback pin has to read that peak, and that's how it regulates. So if you have super, super low ESR capacitors on the output side, you're basically going to clamp the output of your LC filter to where there's basically no ripple, and your regulator won't be able to regulate, and it'll go haywire. It'll switch on, switch off. So you do have to keep that in mind. And this is where I said the data sheet is pretty trash. It doesn't say what the ripple needs to be, at least not that I could really see. They mention that it has a constant on-time architecture with a proprietary emulated ripple mode that allows for the use of low ESR output capacitors, which is fine and dandy, but you go into the design docs at the end, and they do mention what the ESR has to be the minimum, and then it'll also talk about the maximum, and then using a feed forward capacitor. So realistically, all that gobbledygook at the top might let you use a low ESR, but it still has to have a certain value. So the feed forward capacitor helps remedy that a little bit. And another thing you can do on the capacitors, which I might end up doing, is you can add a dampening or damping resistor to the bottom side of the capacitor. which effectively makes it worse, but it allows you to fine tune the ESR to make sure you have enough ripple. They have these spec'd as tantalum or tantalum caps, polymer caps, OSCON caps, or aluminum electrolytics, which are fine. I didn't want to use an electrolytic because it would have been too tall. I didn't want to use a tant because they scare me. And even though it's on the output side, there shouldn't be a lot of inrush. I still pretty much make it a rule that I don't use those in designs. So what I ended up using is, it's crazy how advanced ceramic capacitors have gotten. Like, it's honestly crazy to think that you can go out and buy a 1210 size ceramic, so not even that big, that has a 220 microfarad rated capacitance with an effective capacitance at 5 volts of 70.3 mics. And I know I said I like to have a 2 times D rating. That's mainly on the input side, solely because the input side is where you have to worry about most of your transients. The 5-volt side is quite regulated, and there's going to be Zehners on all of the outputs. There shouldn't be a lot of inductance on any of the traces. So I feel pretty good about that. In ceramics, you can run right at the rated voltage. It's not going to damage them over time like electrolytics. But if that was a concern, obviously you could switch these out for a smaller value that has a higher voltage. And like I said, the issue with this is these have a very, very low ESR. So at the frequency we're going to be running at, which is 500-ish K, we're talking 3 milliohms, which, again, I don't know what value this needs to have based on their data sheet. But if you go to the ESR, they want it to be between 3.5 and 7. I don't really know if that's per cap or combined. I'm assuming it's combined because it says total ESR, but it's not really explicit. If it's individual, I mean, that really honestly wouldn't make sense. But if it is combined, that means what I am doing is 3 milliohms, 3 milliohms, 3 milliohms in parallel, which makes it very, very low. So realistically, I will end up putting on, if not on all of them, at least one or two, a resistor right here. That then lets me fine tune the ESR a little bit. And then for the final version, either do a more sophisticated like ripple injection or just keep the resistor. Doesn't really matter. So that's pretty much the 5-volt buck. The 3v3 LDO is obviously super straightforward. And then the 1.15 volt is another buck. Did the same thing with WeBench. Since this is a lot lower current, it has the integrated FET switch, but everything else is pretty much the same. Again, same gotchas with the DC bias on the input side. These, I believe, yeah, they're the exact same capacitors that I used for the 5-volt buck. So they'll have the 3.8 mic capacitance on them. And again, keeping them within range of what is needed for the inrush and the switching surges. And then what is in the input filter, I'm not going to go into that in this video. Basically, it will primarily be keeping the switching noise confined to the board, because no matter how well of a filter you have here, without some sort of series element, you're going to have some sort of high frequency noise leaving the board, which is obviously terrible. And then also handling transients. But that is the bulk of the power side. The V-Bus, like I said, handles the splitting of the current or the power rails for each of the 4 ports. It has some bulk capacitance for the V-bus on the USB port, and I won't go into the TVS side here, but on the V-bus end, we have a little bit more bulk capacitance. That is something, if you guys have any app notes on, I would love to hear it. I really haven't I haven't done any high power USB stuff before, and it's really hard to find information on capacitance for a downstream facing port. For an upstream facing port, they have limits to how much capacitance you can have, which is like 10 mics or 5 mics. So I know whatever is going to be plugged in here isn't going to have a massive inrush. So I'm assuming by just having the 20 microfarad here and then 20 microfarad on the V-bus to share between these two is plenty. But if you guys have any thoughts on that, please let me know. But that will pretty much wrap up this video. Like I said, the next and final video will cover the input filter. It will cover the TVS and filtering on the output side, and then probably just a quick higher level conclusion. And after that, I will finally go into doing the layout, which the layout I'm planning on doing, if not exclusively on live streams, the majority on live streams. I really enjoyed doing it that way, and it takes a lot less time to do it because I don't have to record it separately. But that is what is going to be coming up. And again, if you have not joined the Discord, the link is in the description. And I thank you, as always, for watching, and I will see you in the next video.